Hi, this is Rohan from educator.ai. Let's dive in. A language model can't multiply the word cat. It only does math on numbers. So somewhere between your text and the model's arithmetic, words have to become numbers. In this video, we'll build the exact mental model for how that happens. Embeddings. First, text is split into tokens, small chunks of characters, and each token gets an integer ID. But an ID like 9084 is just a label. The number 9084 isn't bigger or better than 12. What we really want is a representation where similar words end up as similar numbers. That's the job embeddings solve. Here's tokenization in action. The sentence "the cat sat" splits into 3 tokens, and each maps to an id in the model's vocabulary. These ids are just addresses. The number itself has no meaning. So how do we breathe meaning into them? Think of a map. A city becomes a pair of numbers, latitude and longitude. And crucially, cities that are near each other on the map tend to be similar, same region, same climate. Embeddings do exactly this for words. Each word becomes a point in space, and being close together means having similar meaning. Here's the mechanism. The model holds a giant table, one row per token in the vocabulary. To embed a token, you simply take its ID and look up that row. Row 3797 is a list of numbers, the vector for cat. No calculation, just a lookup, but the numbers in that row are learned. At the start, that table is pure random noise. During training, the model repeatedly tries to predict text, and every mistake nudges these vectors a little. Over millions of steps, words that behave similarly get pulled towards similar numbers. Nobody hand labels, meaning the geometry emerges from the task. Let's watch the space fill in. Here are 4 animal words, and notice they cluster together in one corner. Kitten sits right next to cat. Puppy hugs dog. The exact axes don't have names we picked. They're learned features. But the important thing is that nearness on screen means similarity of meaning. Now add some fruit. Watch banana, apple, and mango land in a totally different region, far from the animals. So the space isn't just about closeness. It also encodes separation. Unrelated topics drift apart, and that gap between clusters is itself meaningful. It's not only distance that matters, direction does too. Picture an arrow from the origin to each point. Cat and dog point roughly the same way, while the fruit arrows swing off at a very different angle. That angle between 2 vectors is what we'll measure to score similarity in a moment. This is why embeddings are so useful. Drop in a new word puppy and just find the points closest to it. Its nearest neighbors are dog, cat, and kitten, the animals, not the fruit. Semantic search, recommendations, and retrieval all rest on exactly this. Turn things into vectors, then find who's nearby. One honest caveat: I've been drawing 2 dimensions so we can see it. Real embeddings live in hundreds or thousands of dimensions, 768, 1536 and up. That count is a design choice, fixed when the model is built. More dimensions give room to encode more subtle distinctions, but the intuition of nearness and direction carries over unchanged. Let's confirm the direction idea in code. Cosine similarity measures the angle between 2 vectors. 1 means pointing the same way, 0 means unrelated. We compare cat to kitten and cat to banana. You'll see cat and kitten score near 1, while cat and banana score much lower. Exactly the geometry we drew. In practice, you rarely build the table yourself. You call a model, hand it text, and get back a vector. Here, a real embedding model returns a list of 1536 numbers for our sentence. That single vector is the whole meaning of the input, ready to compare against others with the same cosine trick. A few traps to avoid. The token ID is just an address into the table. It is not itself the vector. The individual axes almost never map to a tidy human concept like size or color. Meaning is spread across all of them. And vectors from different models have different dimensions and geometry, so you can never compare them directly. Here's your review lens. On the left, the healthy habits. Look up the learned vector, compare with cosine similarity, stay inside one model space, and treat the dimension count as fixed. On the right, the real bugs. Doing arithmetic on raw ids, over-interpreting a single axis, mixing vectors from different models, or assuming a bigger id means anything at all. So the whole picture in 4 lines. A token id indexes a learned row in the embedding table. Meaning is encoded as direction and distance in that space. Similar meanings sit close together, which is what powers search and retrieval. And the number of dimensions is a design choice you inherit from the model. That's embeddings words finally turned into geometry.